I love chemistry. It's beautiful and magical, basically real-life potions. However, in school it is often mystified and made very, very dull. But today's project is some easy chemistry. All you need to know is that atoms, like these hydrogen and oxygen atoms, can connect together with bonds to form molecules, just like Lego. I want to create a tool to visualize molecules. So what I have here is just some coordinates for a bunch of atoms in a very pretty compound called benzene, and it's just the carbon atoms, and I'm visualizing them as circles in Pygame. Now it doesn't look much like a molecule, but if I connect them together with some lines, it starts to look a little bit like a molecule. But this is just flat, so I want to make it 3D, and that's going to involve some transformations. So here's just the bit of code that I've used to translate or transform each atom position. It just takes the vector or position of the atom and alters each one iteratively by a given matrix that will rotate it in the y-axis or the x-axis. And if we want to recenter, we take the position around which we want to recenter and we just subtract that matrix from each of our vectors. Now you can see that by scrolling the mouse wheel, I've basically got our magnification to increase and decrease, but also by clicking and dragging the mouse, we can rotate the molecule in both the x and y dimensions. And here you can see it with methane. I've used the Z component to actually make the circles a bit smaller if they're further away and a bit larger if they're closer. Or it's time to make things a little bit pretty. I've got the covalent radii here of a bunch of the elements, and that will help us draw those circles so that we can scale them a bit to the element. And as well as the radii, I've also got some colours here to highlight different elements. When I get Pygame to draw the circle, we also get the radius from here, and we get the colour based on the type of atom. Okay, so we can see our methane here now with the carbon in the middle, and the hydrogens is just the white circles around the outside. And here we've got paracetamol, and you can see it's not centered well, so I had to use that recenter on one of the carbon atoms here, and now the molecule's nicely centered, and we can spin it round, we can inspect it in quite a lot of detail. But I didn't like the fact that the centering was just on an atom, so I actually changed it to be position based. You could center anywhere, either the center of a ring or off the edge of a molecule. I wanted to import some new molecules, so we have one of my favourites here called azulene. It's a really interesting aromatic compound, but at the minute we're seeing everything as single bonds, so it can be handy to show additional bonds. So I just toggled that with B. Basically you can select whether you see them or not just by pressing B. And then for some large molecules like penicillin here, sometimes seeing all the hydrogens can be a bit tricky to visualize what's actually going on in the structure of the molecule. So by pressing H, you can just hide them. And I set up this little spinning function so that you could just set the molecule spinning and admire your favorite compounds as they go round. So it's all great drawing these molecules, but it'd be really nice if we could use, say, a big online database to pull in molecules. So what I've done is set up just this simple pipeline where you can have a query from the user, and that will go to a local database. Basically it's just a JSON file with a bunch of molecules in it. If we find our molecule in there, then we boot up the program with the molecule visualize. But if we can't find it in there, we send out a call via an API to the PubChem database, which has a huge array of molecules, and if we find it there, we'll visualize it in the program. But as well as doing that, we'll update that local database with that molecule so that we don't have to keep sending out requests to the PubChem servers. So let's see how this works. Okay, so when you run the program, you get a prompt asking you to type the molecule name. So we can put in ibuprofen, and we didn't have that in our database, but PubChem does, so it's imported it and also updated our local database, and now you can see here's ibuprofen. So let's have a look at some other examples, and we can run the program again, and here we get the prompt. So let's have a look at phenanthroline, and you'll notice here I actually spelt it wrong, and that's quite handy to show you something. It was a mistake, but it's handy to show you this, that we couldn't find it because it wasn't there, but now we spell it correctly, and hey presto, we've got phenanthroline. Again, another fun planar aromatic compound. And in honour of one of the most exciting chemistry channels on YouTube, we of course have to look up Nile Red. And here is that really interesting compound, beautiful colour, and of course a very handy indicator. Anyway, that's enough of that. It's time to seamlessly segue into a different topic. I wanted to create a normal collider but where the atoms could collide, and instead of bouncing off each other, they can do that, but they can also react, and we could see what molecules we'd get. And here you can see two of them come together, two hydrogens, and we've created H2. But you see it's moving really slowly. Now it should really make perfect sense why we can't have a bond forming reaction that is also an elastic collision. Because typically when we have an elastic collision, we'll get a vector for each particle or atom moving away from each other. But if we have a bond present, they can't move away from each other. So either this bond has to break or our molecule stays together. This reaction, because it's bond forming, is very energetic. So we'll have an exotherm. And this can be represented by effectively just adding a high magnitude vector with a random direction to our newly formed molecule. If this sounds a little suspect, that's because it is. But it's a nice way of mimicking this to begin with. Okay, so we've implemented that energy increase once the bond formation happens. Right, let's scale this up and see how it copes with more atoms. There we go, that didn't take too long, and I have to say it's kind of reassuring that the model is predicting that hydrogen atoms are not stable, they like to form dimers, and so far things seem to be relatively stable. So let's add in some oxygen and see what happens. You can see that oxygen's reacting to form water. I thought it was really cool just to visualize this as bouncing around. You can see here that two oxygens have come together while there's a hydrogen attached, and if we're lucky, that will end up forming peroxide or hydrogen peroxide, often in bleach. There we go. Well, I have to say, I'm super thrilled with how this is performing. I'm going to leave it here for now. I hope you'll find these projects exciting. If you are, why not subscribe? And I'll leave you with some hydrogens bouncing around. See you in the next one. Bye!